today we shall take up a preparation, properties and the uses of three of these acid derivatives, which are acid chlorides, acid amides and acid anhydrides, and then we will summarize our today's work. We had discussed earlier that OH group of the carboxylic acids can be replaced by some other groups, that is by chlorine or by NH2 or by the alcohol part or from another carboxylic acid. We get different acid derivatives which are called acid chlorides, acid amides, esters and then acid anhydrides. We discussed in our previous session about their nomenclature, that is how they can be named according to IUPAC system as well as common system. We discussed their physical properties and we also discussed that these groups can be displaced and all these compounds undergo a class of reaction which is called as nucleophilic acyl substitution, and based on that we compared that which of these is most reactive and which is least reactive, and we had found that acid chlorides are the most reactive whereas acid amides are least reactive, and acid chlorides can be used for the preparation of all other classes of these acid derivatives. So, today we are going to take the methods for the preparation and their important reactions one by one. First, let us take acid chlorides. Acid chlorides are obtained from carboxylic acids and the OH of the acid can be replaced using thionyl chloride, phosphorus trichloride or phosphorus pentachloride. When thionyl chloride is used, then sulfur dioxide and HCl, these are obtained as the product and both are gases. So, this is considered as the best method for the preparation of acid chlorides because in this no other side product is formed. These two products which are obtained as side products are gases and they are lost. So, if we use the calculated amount of acid and thionyl chloride, we will get pure acid chloride, although PCl3 and PCl5 are also commonly used. We will discuss the mechanism of these preparations. When a molecule of carboxylic acid reacts with thionyl chloride, here this oxygen or this oxygen, any of these can act as nucleophile. They attack the sulfur and one of the Cl, this first in the pair of electron goes to this oxygen, and then in the second step when this pair of electron comes back, one of the chlorine is lost. So, basically what has happened, the acid molecule has displaced one chlorine from thionyl chloride, and this oxygen, since it acquires a positive charge, when this Cl minus is leaving, it takes away the H plus from here and we get a chlorosulfite anhydride. Now, this compound is attacked by another chloride. This chloride is one that is already lost from here, or it can be the chloride from the same molecule, that is this chlorine may attack here, as you have studied in SNI type of mechanism. So, chloride attacks here and we get this pair of electron shifting to this oxygen, and when this pair of electron comes back, then CO bond breaks, this is lost as sulfur dioxide. If this Cl was the same which was attacking here, then this Cl won't be there, and what we get R C double bond O Cl and then sulfur dioxide, and if it is this Cl minus or the HCl we already obtained, any of the two steps can go from here onwards. The similar type of mechanism is there when we use PCl5 as the reagent. Here also either this oxygen or this oxygen of the hydroxyl can attack the phosphorus, one of the Cl is lost, this Cl will capture this H which is causing the positive charge on this oxygen of the acid, we get this intermediate. Here this HCl that was formed here may even protonate this oxygen, means HCl is not lost, H plus is there. So, from this step or this step, Cl minus will attack on the carbon, and then ultimately this POCl3 is lost. What happens? This, when pair of electron from the oxygen comes back, this CO bond breaks and it forms P double bond O. The steps are exactly identical as it was the case in thionyl chloride. The only difference is that here it was sulfur with 1 double bond oxygen, 2 chlorine, it is phosphorus with 3 chlorine, and then 2 chlorine here, which are lost one by one. In the reaction with PCl3, one of the oxygen of the carboxyl, whether this OH oxygen or this oxygen, acts as a nucleophile, attacks PCl3, displaces one of the Cl minus, and then this Cl minus attacks this carbon, and ultimately it leads to the formation of PCl2OH. When this bond breaks, this CO bond breaks, this oxygen goes with the phosphorus. The only benefit of using PCl3 is that one molecule of PCl3 can react with 3 molecules of carboxylic acid one by one. But the reaction with PCl3 is at a little slower rate in comparison to that with PCl5. The same reagents can be used for the preparation of aromatic acid chlorides also from aromatic acid. That is, benzoic acid can be converted into benzoyl chloride using the same reagents, thionyl chloride or PCl5 or PCl3. Aromatic acid chlorides can also be obtained by another method in which phosgene is used as a reagent. The aromatic compounds are treated with phosgene and the reaction is related to Friedel-Crafts acylation, such as benzene, when it is treated with COCl2, that is phosgene, in presence of aluminum chloride, then the COCl group is introduced on the benzene ring and we get benzoyl chloride. But this method is useful only for the preparation of aromatic acid chlorides. Then we talk about their reactions. I said before that acid derivatives, including these acid chlorides, this group can be displaced by a nucleophile, and we have discussed in our previous session that the best leaving groups are halogens amongst different acid derivatives. So, acid chlorides are very easily displaced by other nucleophiles, and nucleophile gets substituted over here and we get other acid derivatives. One reaction we discussed, hydrolysis of acid chlorides. Water acting as nucleophile can attack this carbon and displaces this Cl ultimately in these two steps. First step, electron pair will go to oxygen, and when this electron pair comes back, the Cl will be lost and this Cl will capture this H from this OH. We will get carboxylic acid. This is the hydrolysis of acid chloride with simple water. This reaction can be catalyzed by an acid or an alkali also. When there is an acid present as catalyst, it will protonate this H plus first, so that this transfer of electrons very fast. The positive charge on this carbon is increased, and if it is an alkaline medium, then hydroxide ion itself is a stronger nucleophile, attacks at a very fast rate on this, and reaction is very fast with the catalyzed by acid or by an alkali. Then these acid chlorides can be converted into esters. They react with alcohols or phenols and esters are formed. Since in this reaction a loss of HCl molecule occurs, obviously we require the presence of some base, and generally pyridine or any other tertiary amine is used as a base for this reaction. Phenols also react with acid chlorides and we can get corresponding esters. Say if it is ethanoyl chloride and phenol, we will get phenyl ethanoate. We can have even aromatic acid chlorides reacting with alcohol. Say ethanol reacts with benzoyl chloride and we get ethyl benzoate, or even this cyclopentane carbonyl chloride that reacts with say 2-propanol and we will get this ester, that is 2-propyl cyclohexane carboxylate. So, all type of esters can be obtained by the reaction of alcohols or phenols with different acid chlorides. Acid chlorides can be converted into amides also. The simple amides are obtained when acid chlorides are treated with ammonia or stronger base like sodamide. They react here and displace ultimately chlorine. Then amides can be obtained on the reaction with other amines also. But when any amine will react, then we will get a secondary amide or tertiary amide. Say if it is a primary amine reacting, that is amine with one alkyl group, then we will end up with a secondary amide. Acetyl chloride reacts with methylamine. Now this nitrogen acting as a nucleophile displaces this chlorine and we get N-methyl ethanamide. A secondary amide is formed. Then we can get anhydrides also from acid chlorides. Acid chloride react with carboxylic acids. Again a molecule of HCl is to be lost in this case, and obviously this reaction is helped by the presence of some base like pyridine. Acetyl chloride reacts with benzoic acid in presence of pyridine and we get acetic benzoic anhydride. If in place of using directly acid, we use the sodium salts of acid, then no need of base is there. The sodium salts of acids, they react with acid chlorides and a molecule of NaCl, sodium chloride, gets precipitated and we get corresponding anhydride. Say acetyl chloride on reaction with sodium formate gives us acetic formic anhydride. Then there are some other reactions which are specially shown by these acid chlorides. One of them is the reduction to corresponding aldehydes, and it is a name reaction called Rosenmund reduction. In this Rosenmund reduction, the catalysts are palladium hydrogen, that is, it is catalytic hydrogenation basically, but we use a small amount of barium sulfate in it as a catalyst poison because we do not want to reduce this C double bond O. Only Cl is to be reduced and Cl is replaced by H. So acid chlorides get converted into corresponding aldehydes. These acid chlorides may be aliphatic as well as aromatic. So benzoyl chloride also undergo the similar reaction and we get benzaldehyde. Then these acid chlorides can be reduced to aldehydes by another reagent also, which are tri-tertiary butoxide derivatives with lithium and aluminium. So actually we name these compounds as lithium tri-tertiary butoxide aluminium hydride. Such as isobutyryl chloride, it undergoes this reaction with tri-tertiary butoxy aluminium hydride to give corresponding aldehyde. Then acid chlorides react with Grignard reagent also, and when the reaction with excess of Grignard reagent is carried out, 2 moles of Grignard reagents are used and ultimately we get tertiary alcohols. So this is an acid chloride. First molecule of the Grignard reagent, say we have taken methyl magnesium bromide, the methyl goes here and then Cl is lost, we get a ketone as intermediate, then another molecule of Grignard reagent reacts, one more methyl goes here and then ultimately it becomes OH when finally we treat it with water. So here we get this tertiary alcohol. So Grignard reagents are converted into tertiary alcohols. They may react with sodium azide and corresponding acid azides are obtained. The Cl is replaced by this N3. Acid chlorides can be used for the preparation of ketones also, and the benefit of this reaction is that we can get unsymmetrical ketones very easily, means those ketones which have 2 different groups, such as this acid chloride, they are treated with dialkyl cadmium. So we can have this different alkyl group and here a different alkyl group, and one of the alkyl from dialkyl cadmium replaces this chlorine and we get ketone. These dialkyl cadmium compounds themselves are obtained from Grignard reagents. Grignard reagents react with cadmium chloride to give us corresponding dialkyl cadmium. So this reaction is different from the direct reaction of acid chloride with the Grignard reagents. There we are getting tertiary alcohols, here we are getting ketones, and benefit is we can get unsymmetrical ketones as well as symmetrical ketones. It is our choice that we can have the similar alkyl groups or different alkyl groups. Then acid chlorides can also be converted into ketones on treatment with dialkyl copper lithium compounds. Here also we can have same alkyl group or different alkyl group to give the suitable ketone. We can get aliphatic aromatic ketones or even aromatic ketones by a Friedel-Crafts reaction where acid chlorides are used as one of the reagents. Aromatic compounds react with acyl chlorides or acid chlorides in presence of anhydrous aluminum chloride. This COR group gets substituted over the ring and we get corresponding ketone. Suppose benzene is treated with benzoyl chloride, we will get benzophenone where both the groups are aromatic. Had it been any other aliphatic acid chloride, we will get corresponding aliphatic aromatic ketone. So, acid chlorides are useful intermediates, this we had discussed earlier also, for getting all these compounds acids, esters, amides and anhydrides. Then uses of acid chlorides. Acid chlorides are used in organic synthesis to introduce acyl group into other compounds also. One use we have seen that we can synthesize all other aromatic compounds, then we can introduce acyl group in many other aromatic compounds, and these acyl groups are also used as a protecting group in organic synthesis. The most commonly used group is acetyl group that is introduced on treatment with either acetyl chloride or acetic anhydride. Next we move on to acid amides. These acid amides can be prepared directly from carboxylic acids. Carboxylic acids are treated with ammonia. Initially we get ammonium salts of carboxylic acid, we call them as ammonium carboxylate, and these salts on strong heating get converted into amides. They lose the water molecule. We have discussed just before that they can be obtained from acid chlorides also. The acid chlorides, they react with any amine, this can be simple ammonia also, in a similar way that ultimately this Cl is to be lost and we get corresponding amides. If we use some amine, we will get substituted amides. If it is simple ammonia, we will get primary amides. One example is say propanamine. It is treated with ethanol chloride, then we get this N-propyl ethanamide. Then there is another related reaction to it, is called Schotten-Baumann reaction. When both the reactants are aromatic, that is we take an amine that is aromatic such as aniline, and the acid chloride is also of an aromatic acid chloride, say benzoyl chloride, then reaction is carried out in presence of aqueous base like sodium hydroxide and this benzamide is obtained. This reaction becomes very fast because of the presence of a strong base like sodium hydroxide. Then we can get amides by the ammonolysis of acid anhydrides as well as that of esters. Acid anhydrides get cleaved when treated with ammonia. One of the part goes as amide and another part goes as acid. Similarly, esters, they also react with ammonia to give amides and this alcohol part is left. Basically, ammonia replaces this alcohol. Then they can be obtained by partial hydrolysis of cyanides. Cyanides are the compounds with having triple bond between carbon and nitrogen, and this CN is partially hydrolyzed to give amides. Complete hydrolysis will ultimately leads to the formation of carboxylic acids. Then reactions of amides. Amides are hydrolyzed. We have discussed earlier that all these acid derivatives can be easily hydrolyzed in acidic medium as well as an alkaline medium to give corresponding acids. So, hydrolysis of all amides gives corresponding carboxylic acids. Amides can also react with nitrous acid. You are familiar with one of the reaction of primary amines with nitrous acids, they form diazonium salts, and reaction is called diazotization. It is a similar reaction, but this diazotization of these amides gives an unstable product which immediately loses nitrogen and we get corresponding carboxylic acids. Then again there is an important reaction of amides which is called as Hofmann-Bromamide reaction. This reaction involves the conversion of amides into amines with one carbon less than those present in amides. actually this CO is lost as carbon dioxide during the reaction, and whatsoever amide we have, we will get the corresponding amine, but having one carbon less than the starting compound. This is the steps involved in this reaction. This amide is treated with bromine in presence of NaOH. In the first step, bromination occurs here. It forms NHBr, and then alkali takes away this Br as Br minus, and simultaneously this alkyl group migrates to this nitrogen, because nitrogen acquires a positive charge when this bromine is polarized, and we get this R from here, then N, and then double bond C, double bond O, isocyanates, and these isocyanates get hydrolyzed to give corresponding carbamic acid, which lose carbon dioxide to form primary amine. So, starting from any amide, we will get a primary amine with one carbon less. Reaction is called Hofmann-bromamide reaction. Another reaction is dehydration of amides. Amides can be dehydrated on heating with P2O5 or other dehydrating agents like POCl3 to give corresponding cyanides. Then reduction of amides. In amides, this CO group is reduced into CH2. So, again we get primary amines from the primary amides, but here our amine will have the same number of carbon atoms as in the starting amide. And the reducing agents which are generally used are lithium aluminum hydride or sodium in presence of ethanol. If we have any secondary amide here, we will get correspondingly secondary amine here, such as N-methyl ethanamide. When this is reduced, this CO will be reduced into CH2 and we will get a secondary amine, that is methyl ethanamine. Then uses of amides. Amides are less reactive, so they resist hydrolysis and provide structural rigidity, such as in proteins and polyamides like nylon. Another naturally occurring polyamide like silk, these are quite strong fibers. Then lower amides like dimethyl formamide and dimethyl acetamide, they are used in paint removers. They are used as solvent for plastic, resins and gums. Dimethyl formamide is also used for removing the stains of ballpoint ink on clothes. Many drugs such as penicillin have amide bonds in them. Amides are also used in the synthesis of many dyes, adhesives, paper and textile, and they are also used in sewage treatment. Many amides possess insect repellent properties also. So, this is about amides. Next we move on to acid anhydrides. Acid anhydrides are obtained from carboxylic acids by the loss of water. Two molecules of acids, if they react and a loss of water molecule, we will get corresponding anhydride, and this loss of water molecule is assisted by dehydrating agents like P2O5. Some dicarboxylic acids like succinic acid, even on simple heating at high temperature of the range of about 300 degrees Celsius, lose a water molecule. We do not need any dehydrating agent. So, succinic acid gives succinic anhydride. Similarly, phthalic acid, which has got two carboxyl group ortho on the benzene ring, also on heating loses a water molecule and we get phthalic anhydride. So, dicarboxylic acids give these anhydrides bit easily. Then carboxylic acids can also be converted into anhydride using ketene, but in this reaction we will get anhydrides which on one side will have only the acetic acid part, such as any acid RCOH when it is reacted with ketene. Ketene is a compound CH2 double bond C double bond O, and in this actually what happens during the reaction, this OH bond breaks, this H goes to this carbon and remaining O with minus goes to this carbon. So, this ultimately gets converted to C double bond O CH3, this part. So, we will get anhydride which have one part like that of acetic acid and another for any other acid. So, this is also a good method for the preparation of anhydrides. Then anhydrides can be obtained from acid chlorides also. Carboxylic acids, they react with acid chloride in presence of a base like pyridine, we get acid anhydrides. Then sodium salts of the carboxylic acids, they react with acid chlorides, they lose NaCl molecule and we get acid anhydrides. As far as the reactions of acid anhydrides are concerned, one common reaction for all acid derivatives is hydrolysis. So, anhydrides are also hydrolyzed in acidic medium as well as in basic medium to give corresponding acids. If it is a symmetrical anhydride, we will get the two molecules of the same acid. If it is an unsymmetrical anhydride, we will get one molecule each of the different acid. Then ammonolysis, acid anhydrides react with ammonia and one of the molecule goes as amide and another as carboxylic acid. Then esters are also obtained from anhydrides very easily, because in the reaction series of these acid derivatives, the most reactive are acid chlorides and then next are acid anhydrides. So, alcohols or phenols, they react with acid anhydrides and we get corresponding esters. The alcohol or phenol act as nucleophile, attack the carbonyl and one of the acid part is lost. One of the important reaction of phenols is the salicylic acid. It reacts with acetic anhydride in presence of few drops of sulfuric acid and we get this acyl derivative here, and this is a very useful medicine, aspirin, that is obtained by the acetylation of salicylic acid. Then their uses, these acid anhydrides are used in organic synthesis to introduce acyl group into other compounds as acid chlorides are used. Then succinic and malic anhydrides are used for the synthesis of various resins, and phthalic anhydride is used for the manufacture of many dyes. They are also used in pharmaceuticals, agrochemicals and photographic chemicals. So, in our today's session, we reviewed our work of the previous session, and then we discussed the methods for the preparation of acid chloride, amides and anhydrides. We talked about their properties, some important reactions and their important uses.